Hi, my name is Ethan Nowaski, and this is the Week 2 explainer video for Problem 40, Chapter 14. Postural hypotension is the occurrence of low systolic blood pressure when a person stands up too quickly from a reclining position. A brain blood pressure lower than 90 millimeters can cause fainting or lightheadedness. In a healthy adult, the automatic constriction and expansion of blood vessels keep the brain blood pressure constant while posture is changing, but disease or aging can weaken this response. If the blood pressure in your brain is 118 millimeters while laying down, what would it be when you stand up if this automatic response failed? Assume your brain is 40 centimeters from your heart and the density of blood is 1,060 kilograms per meters cubed. So we have our givens right here, which is our pressure 1, P1 is equal to 118 millimeters. Then our difference of Y, which they gave as 40 centimeters, right here. And then we have our density of blood, rho, is 1,060 kilograms per meters cubed. I'm trying to find the pressure in the brain after standing up, or P2. We know that rho, we should be very careful that rho is not equal to P1 and rho is not equal to P2. These are very different variables, even though they look similar. Rho is the fluid density and P is the pressure. So we can look at the difference of flow right here because it's flowing normally as you're laying down, and then that change is very dramatic once you stand up, because your heart has to pump the blood up instead of just along a horizontal line. So to solve this problem, we need to look at Bernoulli's equation. And this is a very important principle in fluid dynamics because it shows us the relation between kinetic energy, potential energy, and work, and how this applies with fluid dynamics. So we can see how our equation for change in kinetic energy converted into fluid dynamics form, which is 1/2 rho volume v2 squared, or velocity, minus 1/2 rho volume v1 squared. And then we have our potential energy, which is mgy2 minus mgy1, which converts to rho v, or rho volume gy2 minus rho volume gy1. Then we have our work 1 plus work 2, and this converts to P1, or pressure 1, minus pressure 2 times volume. And this gives us our kind of modified equation of Bernoulli's equation, which we can then easily change by dividing out the volume, which it has in all of these, so we can know we can do this, to get this modified version of Bernoulli's equation, which is 1/2 rho v2 squared minus 1/2 rho v1 squared plus rho gy2 minus rho gy1 is equal to P1 minus P2. So when we use this equation, we have our givens as well, and we can try to convert this equation into something that actually helps us. So first things first, we know is that the velocity, the V2 and V1, is going to remain the same in the blood either way. So we know that these two parts can actually cancel out. So what we're left with is the rho gy2 minus rho gy1 is equal to P1 minus P2. And we can separate out the rho g, and then we get P1, and then if we solve a little bit more to get equal to P2, we get P1 minus rho g times delta y, because y2 minus y1 is delta y, is equal to P2. And then we have all of these variables except for P2, which we can actually solve for. And if we put all of our variables in, we will get 118 millimeters of blood minus 4,155.2 PA, and this is the pressure units. But we know from the book that this pressure units converts using this conversion, and if we multiply these two, and then we subtract it from 118, we get 87 millimeters of blood is equal to P2. And from our question, if we recall, that it is, if it's less than 90 millimeters, then you might experience fainting and lightheadedness, which we know this person might if their automatic system does not respond. So thank you.